Hey guys, welcome back to my AP Biology Minecraft Let's Play, and today we are copying topic 8.5, Community Ecology. It's going to be a fire video, guys, so let's dive straight into it. So what will we learn today? So today we're going to cover several topics, including how to measure community structure, what determines how a community changes over time, how populations access matter and energy, how relationships between communities are characterized, what types of interactions drive population dynamics, and how community structure relates to energy availability. So without further ado, let's get into it. So first up, we're going to discuss how species composition and diversity relates to community structure. So a community is a group of organisms that live together in the same location and interact with one another. The stability of community relies on both species composition and diversity. Species diversity is the number of species and quantity of each. So let's look at an example down here. If we go down here in this coral reef, we see for our species diversity, we have tropical fish and sea turtles only. We have about 5 sea turtles and quite a few of tropical fish. So that would be the diversity. Species composition, however, refers to the specific species present. So we may have one species of sea turtle, but we have several species of tropical fish, as you can see here. You can see that by their physical differences, like their color, shape, etc. So next up, we'll see how we can mathematically measure the biodiversity of a habitat. The Simpson's Diversity Index measures the biodiversity of a habitat with a larger final value, meaning the area is more biodiverse. So this is the equation. So D, meaning diversity, equals 1 minus the sum of small n, which is the specific members of one species, the amount of organisms of one species, divided by big N, which is the total number of organisms of all species, squared. So as you can see here, and we add all these together, subtract from 1, and the closer the value is to 1, meaning the larger it is, the more diverse the habitat is, and the closer it is to 0, the less diverse it is. So let's do an example with this lush cave biome we got right here. So you can see we have quite a lot of organisms. We got even some here. And let's do a count. So we have 6 different species here, and we have 44 total organisms. We have 7 axolotls, so these little salamander dudes. We have 10 zombies, 4 creepers, these green guys, not these ones, these bright green ones, 12 skeletons. We have 8 fish over here that are part of this, and we have 3 slimes, these small little green dudes. So if we plug these values into the formula here, we get a final value of 0.82, which means this cave is actually fairly biodiverse because the value is quite close to 1. Alright, so a bit of a change of scenery here. Next, we're going to talk about how organisms interact between populations. Interactions are important because the communities change over time based on these interactions, mainly driven by competition between members of a species of a population. These interactions can be positive, negative, or neutral. So let's take a look at a positive one first. So it's called mutualism. Mutualism is when both organisms benefit, and let's have an example here. So we have a villager trading hall. So we have some villagers set up here, and this is mutualistic because in exchange for protection and resources like my emeralds, so see, protection from bad guys, as well as exchange for resources, I get rare resources that'd be hard to come by in like the conventional means. So we both benefit. They get protection resources, and I get rare resources that'd be hard to come by any other way. So next up is commensalism. Commensalism is when one organism benefits and the other is unaffected. So an example would be, so say you have your base. So it's my super awesome base. You can see it's very spacious, very luxurious. And say you have your friend here. Whoops. So as I was saying, say you're a friend here in your base. Say your friend decides to suddenly move into your base and just simply live in your base. Now this is commensalism because your friend benefits from having shelter and a place to stay, while you're basically unaffected by his presence alone. So simply him being there does not affect me negatively or positively. So this would be commensalism. Alright, so now we're going to move on to the negative relationship. So our first one's predation. Predation is when one organism benefits from the killing and extracting of resources or energy from another. So here we have my friend, or my enemy in this case, and he has some loot. He has some nice gold in this chest, and I want it. So I'm gonna kill him and then take his loot. So this would be predation because I'm benefiting from the killing of him because I get his loot and his resources and energy. Alright, so our next situation is parasitism. So parasitism is similar to predation in the way that one organism benefits and the others affect negatively, but the negatively affected organism here is not killed, and that is very crucial to the idea of parasitism. So let's take an example. So let's say you're down in the cave. You see you're kind of deep underground, and we're mining some diamonds. So we got our diamonds, and we go back up. So we're gonna go back up to our base and put our diamonds in a chest. So that's our friend, whatever, doesn't matter. I'm gonna put my diamonds in this chest, and then I'm gonna go do something else. Just I'm gonna go farm or something. Try to feed the horse. And when I come back, while I was gone, I realized half my diamonds are missing. I had 10 before, now I only have 5. So what happened? And I guess it's kind of obvious. Our friend, took them. Now, because we now have less diamonds, this encourages us to go back down and mine more diamonds. And then once we put them in the chest, he's just gonna take more. So parasitism works like this, where the parasite drains resources, nutrients, energy, anything valuable from the host, and the host keeps replenishing this, and in our case that's me going to diamonds. So while I have to go do the work and get all these resources, he just gets to benefit without doing any of the work, but he still gets diamonds. And he can't take all the diamonds, because if he took all the diamonds, then I'd have nothing to go back down and get stuff with. So he leaves me with some, just so that I keep getting stuff, and he's benefiting. So our next situation or relationship here is competition. Competition is different in the way that both organisms are affected negatively, so no one benefits. So an example would be, say you were fighting someone. So you're fighting, and even though you beat them, you took damage to your armor. So this is going to cost resources, energy, and time to repair. So look, I had to use one of my experience points down here and also a whole diamond just to repair this. So I may have killed him, but I didn't get anything from killing him, and I only were affected negatively by having to repair my armor and use my limited resources. So in competition, no one benefits. Both parties are affected negatively. For our last relationship, it would be neutral interactions. Now these are the easiest because they're all the same. And a neutral interaction is basically when there's no effect on either organism in the situation. So a pretty easy example would be, say you have your base, you have a nice base, and you're strolling around, and you look to your right, and your friend moved in like just right next to you. Now this would be a neutral interaction because his presence alone near my base, it doesn't affect me positively or negatively, and it doesn't affect him positively or negatively. So his just presence near my base is a neutral interaction. Alright, so for our last topic of the video, we will be discussing the various ways we can model relationships within and between populations, such as predator-prey, trophic cascades, and niche partitioning. So let's look at predator-prey first. So predator-prey relationships form when one organism hunts and consumes another for energy, forming the foundation of a food web. The population cycle follows this relationship and goes as follows. So say we start with a large prey population initially. So we have sheep here, and our predators are wolves. So we have a large prey population with little predators. But if we introduce some predators, so even though we only have a few predators, they're able to take advantage of the large prey size and a large amount of available energy. So as you can see, the sheep population decreases dramatically, and afterwards there will be an increase in the wolf population. So over there we only had 2, and here we have 4, but now there's a lack of prey. So how are we able to sustain? So if there's some prey, they're not able to sustain everybody. There's not enough for all 4 wolves. So that leads to the predator population decreasing and the prey population coming back up. So you can see it increases again, and then it'll go back to its original size that it was before the predator introduction. And the cycle continues on and on. And this is quite a simple demonstration, but in reality it's a lot more complex because we have multiple organisms and we have a whole food web, not just one prey and one predator. the sheep and the wolves again, we're going to look at trophic cascades. So a trophic cascade is the idea that changes to the top or higher levels of the food web have effects on the lower levels. So let's look at a simple level with the top predator being the wolf. So here you can see that we have a bunch of sheep and they're eating the grass, as you can see. Like the grass is going away, it's not as green, and they're diminishing the environment of its resources. So let's add some predators. So before there were no predators, and now that we added predators, so there's a change to the top of the food web, now the prey population decreases. But indirectly, this also causes the population of producers to change. So if we just wait for a second, there, we saw that the grass started to grow back. So the change in the top of the food web was able to bring change to the bottom, directly or indirectly. So we see that the grass grew back. Okay, so because of the lack of prey that was present, now all the grass grew back. There's no brown anymore, just a little bit, but it's mostly green now. But if we so now the predators are gone. We don't know why. Some disease hit the predators. So now there's no predators, so the prey population comes back. And as a result, we're gonna start eating the grass again. Yeah, so right here we can see that one of them ate the grass, so now the grass population, or the amount of grass available, as well as other producers, is going to decrease because there's now a lack of predators. So a change in the top predator, the wolf, had a severe impact on the bottom of the food chain, or the food web, being the producers. For our final topic of the video, we're going to look at niche partitioning. So niche partitioning is the process by which organisms develop different adaptations or uses of the environment to avoid direct competition. And this process allows multiple populations, no matter how similar they are, to coexist. Organisms can divide land, resources, or even time of the day that they're active via this process. So an example would be, say your friend, or your enemy in this case, has a cave. And you want to use that cave, but they're not letting you. You don't want to mess with this guy. He's probably going to beat you, or even then it's just a waste of energy, resources, whatever. So instead of fighting for this cave, you may just walk on over here and go in this cave. Even though it's smaller, you can adapt to benefit equally from this cave as you would from that cave. See? So that is niche partitioning. Alright, and with that, we conclude our community ecology Minecraft Let's Play. I want to thank you for watching, and make sure you like, subscribe, and hit that bell. And I'll see you next time for some more AP Biology. See ya.